Hello everybody, my name is Stefan Lipp. I'm a PhD researcher at the Technical University of Munich, and I'm going to present a paper, an empirical study on the effectiveness of static C code analyzers for vulnerability detection. This is joint work with Sebastian Banesco and Professor Alexander Bretschner, who are both with TUM. Let me start with a brief motivation of our work. So when you look at the CVE reports filed year after year, you will see that C and C++ are still among the programming languages that are most susceptible to introducing vulnerabilities. And to find such vulnerabilities, developers like to use static code analyzers because they are oftentimes less expensive to set up and to execute than dynamic testing tools like fuzzers or concurrent execution engines. However, these static analyzers come with a caveat. So they produce false positives, and this is a common criticism of these tools, and is studied and has been tried to address in many research papers. Our work, however, focuses more on false negatives. So how effective actually are these tools at detecting vulnerabilities? And existing studies that matter, they mainly use benchmarks with artificial security bugs. So these are bugs that come in the form of small syntactic code changes and are therefore rather easy to detect for such tools. And when we look at the evaluation reports or results, we see that the detection rates are around 80%, or for certain types of vulnerabilities even higher. So the main question of our work was, or what we wanted to see is, if these high detection rates that we can observe on these artificial bugs also translate or carry over to more complex bugs that we see in practice or real-world software systems. For our evaluation, we selected 6 widely used static code analyzers, and we can group them into 2 different categories. So we have these syntactic analyzers. Here we have flaw finder. You can see the abbreviation in the brackets here. So what flaw finder is doing, it scans the source code for certain patterns that might indicate a vulnerability. The semantic analyzers, on the other side, they take also the program semantics into account. So they analyze the control and data flow and are therefore supposed to find more complex vulnerabilities. Here we have InfoCodeQL code tracker, which is some kind of front end for the static analyzers provided by the LLVM or Clang toolchain. We also have one commercial tool, which we anonymized here, and we have CPPcheck, which is basically a mixture of both worlds. So it has some syntactic features as well as a lightweight semantic analysis implemented. All right. So the goal of our evaluation was to perform it completely in a automated way, and so that the results are also reproducible. Another goal was to not only check if the tools mark the correct code location, but also if they output the right vulnerability type. And what you can see here is that for the same type of vulnerability, different static code analyzers output different names, which makes it very difficult to evaluate them then in an automated way. So the first step was to map these analyzer-specific names to a common naming scheme. Here we used the common weakness enumeration, in short CWE. And yeah, that is what you can basically see here on the picture. What you've also noticed, that different CWEs are related to each other. So for example, we have a double free vulnerability, which is CWE 415, and we have use of the free vulnerabilities, which are CWE 416. And in an evaluation, you would actually see if a static analyzer, for example, outputs that CW 416 and the run truth states CW 415, you would actually count that as a correct finding. So using these CWEs at that fine-grained level might be too strict for evaluation. So what we did is we created vulnerability classes, and for that we extracted or we used the already existing child-parent hierarchy that is specified with these CWEs. So here, for example, a parent CWE like CWE 825 is, so to say, a more abstract definition, a more abstract or more general description of a vulnerability than these child CWEs. So in the end, we have different vulnerability classes which we can then use to actually check if a vulnerability was found or not. In the beginning of my presentation, I said that we are using real-world software with real-world vulnerabilities specified or reported as CVEs. And here on the left side, you can see the table with our subject programs. Actually, in total, they are 27. Here in the table, we have only 9 because I summarized all those programs in the Benito suite as one row here. In total, we have 192 vulnerabilities, real-world vulnerabilities in our benchmark dataset. And the first 7 programs actually come from the Magma benchmark dataset. So Magma was originally designed for evaluating the effectiveness of fuzzers. It was published in 2021. But since they are providing real-world software with real-world vulnerabilities, we can also use them for our purposes. On the right side, we see the vulnerability distribution of our dataset. We have 21 different types of vulnerabilities that are grouped in 5 vulnerability classes. So here we have vulnerabilities that refer to memory-related vulnerabilities that are grouped in CW664. We have incorrect calculations whose results may then be used in security-critical source code. Those vulnerabilities are grouped in the class CW682. We also have program control flow manipulations so that the security of the program is compromised. Vulnerabilities to these kind of vulnerabilities fall into the category CWE691. The last 2 classes are concerned with, so here the first one, CWE703. These are exceptional conditions that are not properly checked or handled in the code. So for example, we have a forgotten if statement that would prevent a null pointer dereference. Last but not least, CW707. Here program input or output is insufficiently neutralized against security threats, like a mail from string that is passed via a program parameter or an environment variable. These kind of variable vulnerabilities belong to this kind of class. In the beginning, we said that we want to automate the entire evaluation process, and for this we need to agree on a certain code abstraction level that we want to use here. And this is quite tricky because we need to consider 2 different code locations of vulnerabilities. So first we have the root cause of the vulnerability, the code fault, so to say, and on the other side we have the code location where the vulnerability manifests, which might be at different places in the code. And here we need to check what is provided by our ground truth and what is actually flagged by our static analyzers. And here we found out that in order to reduce false positives, static analyzers tend to mark rather the error location, so where it manifests. In our benchmark dataset that is based on CVEs, we however noticed that most of these vulnerabilities are specified as false, so the root cause. They are also specified sometimes by providing only the function, sometimes they provide only the line numbers. So they come at a different level of accuracy, and finding the right abstraction here was pretty difficult, but we agreed on using function level. For our evaluation to work here, obviously, fault and error must be within the same function, and we spent some efforts on showing that for basically all or almost all of our vulnerabilities that is in the case. For further information, please have a look in the paper. So now let's talk about the actual evaluation and the research questions that we are answering here. We have 3 research questions. The first one is basically asking how effective are state-of-the-art tools at detecting vulnerabilities in real-world code bases. The second one builds on top of it and is asking how much more effective can we be when using multiple of these tools in combination than as compared to using only one tool. And the last research question is concerned with the effectiveness of these tools when it comes to different classes of vulnerabilities. All of these 3 research questions we evaluate from different perspectives, from different detection scenarios that you can see here on the right. We have 2 scenarios where we say, okay, a vulnerability is only counted as detected if at least one of the functions that is affected by a vulnerability was marked by the tool. And then we further distinguish between saying, okay, in one scenario we only want the tool to mark the code location, and the second one we say, okay, we want to have the tool to mark the code location and also output the right class of vulnerability. The last 2 scenarios are quite similar. However, here we say, okay, for a vulnerability to be counted as detected, we want the analyzer to flag all functions that are affected by the vulnerability, and then again we further distinguish between the vulnerability class, if it's correctly outputted or not, or if we even want to have it considered here. Now let's have a look at the actual evaluation results. Here for the first research questions, we can see that plot here. On the x-axis we have the different static analyzers that we used in our study. On the y-axis we have the detection rate. We have then, in these different facets, we have the different subject programs, and the bars in these different colors are the different detection scenarios that I just explained. So what we can already see here is that on different subjects, the different tools perform differently, good or badly. For this presentation, I summarized the results as follows. State-of-the-art static C-code analyzers actually overlook a large number of real-world vulnerabilities. So even the top-performing analyzer, which in our case was the commercial tool, fails to detect between 47 and 80%, depending on the evaluation scenario, of the 192 vulnerabilities. Let's have a look at the second research question, where we analyzed the effectiveness decrease that we get when combining multiple tools. Here we used the tools that were most effective, the ones that detected most vulnerabilities in all benchmark programs. That you can see them here on the x-axis, and on the y-axis we can see the values or the bars of two different metrics. The first one, the same as before, here in green the ratio of detected vulnerabilities, detection rate, and in orange the amount of marked functions. In summary, we can say that using multiple analyzers can improve the detection rate by 21 to 34 percentage points compared to a single top-performing tool. However, as trade-off, these combinations roughly flag 15 percentage points more functions as potentially vulnerable. What is quite interesting, that even though we combine these tools, we still miss between 30 and almost 70% of the 192 vulnerabilities in our benchmark, which is still quite a lot. Last but not least, research question 3, where we analyzed which classes of vulnerabilities were detected best and worst. Here you can see the plot. On the y-axis the vulnerability classes, on the y-axis we can see the number of vulnerabilities detected. These are the bars in green, and here on the right side we again have these 5 different vulnerability classes that I explained previously. In summary, we can say that vulnerabilities of the classes CW664 and 703, which are more or less the classical memory-related vulnerabilities, are more effectively detected than those belonging to the remaining vulnerability classes. So it seems like that for these kind of memory-related vulnerabilities, these static analyzers are optimized. Depending on the different scenarios, however, or when we look at those classes that were best detected, still 32 to 66% of the 117 664 CVE CW664 vulnerabilities and 24 to 59% of the 29 CWE703 vulnerabilities again were still missed. Alright, so let me summarize what I've talked about in this presentation here. At the beginning I explained how we are automating the entire evaluation process, and here I explained how we are mapping these analyzer-specific vulnerability types to the CWEs, and then we also use them to create this kind of hierarchy to derive these vulnerability classes, which we then use for our evaluation. We have then talked about the benchmark dataset, which consists of real-world software vulnerabilities with known real-world vulnerabilities. We have talked about these different types of vulnerabilities our benchmark dataset includes, how we can, or which are the classes in which we can group them, and we have also talked about the evaluation results, where the bottom line basically was that many of those real-world vulnerabilities, even though they are supported by the tools, were missed. Regardless if we combine these tools, where we can be a little bit better than just using one tool, but still we are missing quite a lot of vulnerabilities. For more information, please have a look at our preprint, which you can find here in the link on the left corner. Apart from that, that's the end of my talk here. Thank you very much.